you do. And then participants, claim host 103292. So you're the host now. Do you mind if I put this up there to Yeah, you got it.
Okay.
Yeah, like.
Let's connect.
This seems to be convenient, at least from my understanding.
Okay. I have to connect which one?
But at least where I
If
am
you
from,
have, otherwise I have to
it
go to my
becomes
office to bring that.
you can get married only to the thing.
Next side.
It'll need to be on that side.
That's
The USB-C side. And then it'll take a second to connect,
Bad omen. Oh, super sweet.
but let's see. Video, there we go. And then audio. Awesome. And then yeah, you'll need to one more. And then for some reason it's auto mirroring, so video settings and don't mirror. There you go. Cool. Yeah, that's
So
fine.
this will record in my computer.
Yeah, if you want to undo it when the meeting is over or the class is over,
I have to send it, this one to you.
it automatically downloads.
Okay, then no need to worry for me. I have to just check this one is working and.
Stop it. Yeah, just make sure it will work. Yeah.
I'd at least finally put in a meeting ID enough to where I have all the information memorized. It's like the meeting ID, the password, the claim host code and everything.
Okay, I have to copy that.
What will we do after you have it?
Otherwise I have to open the website again. The one is out.
Yeah.
I'm kind of glad to do.
Actually, yesterday we became scared that something that we meeting, so today she will take off for the afternoon.
We'll see us get away.
Yeah. Today she has a meeting with the department at 11:30, so that he will look at my website, so that
Thank you.
Thanks.
Okay. See you there, Big Dog.
See you tomorrow.
Good luck, man.
Thank you. Bye.
I got number one.
Okay. Well, how is everything going? Homework class? Anything?
They're working on
Yeah. the look at-
It's due today, right? So it will be possible.
it. We try.
I'm not halfway through. I'm gonna see if I can by the end of the day. I plan to leave here to go to Georgia for 4:30. So
Today 4:30 and you have to finish this homework?
I'm gonna be here until 4 because I gotta wait for another person I'm taking. We're carpooling. So I'm waiting for them to get done. We can get that today.
How do you manage all this? You could ask the professors not to give homework.
Oh, yeah, exactly.
But it would be so much fun if there are no homework, only
I think that one
marriages
is
to attend festival.
that side. Okay.
I don't know. I might be back. Maybe not here. But I mean, when it happened.
Let me check.
Next
Which side? Maybe.
Oh, yeah, the focus.
Oh,
you're good, yeah.
Yeah.
This line?
Thank you.
Did you guys check the focusing? Is it focused?
Yeah, it's okay.
We start a new concept today, Green's function, so it will be important. So for Jackson and Payne, they have to follow the recording and get it going. So I'll do a simple example today and do the main theory next time instead of doing the opposite, because then it becomes abstract and sometimes it is not convenient. So I'm going to try it this way, that I'm going to do a simple example, solve it, and then motivate the idea behind Green's function in the next lecture. But before that, there's a midterm 2. Lights not on, right? Is the light on?
No, that's it. We have to on that one and that one.
Oh, yeah.
Yeah.
There you go.
So there's homework 8 you next Friday. And midterm 2. I repeat, this is 31st. We changed it back. So make sure all of us register. No excuses. Midterm 2, there usually I try to have midterm 2 contents between midterm 1 and 2, so it doesn't concentrate too much on the earlier. This time I'm thinking of making it cumulative. Is that okay? Check. That means that even whatever we already had midterm 1 on, that I can ask that also. Think about it, and if you have significant reservations that you will lose points, tell me. Why I'm afraid of or why I'm doing it is not because I want to make it harder. It is to make it easier, because I can ask short questions from the content that I asked earlier. Whatever we are doing now, the questions will be longer, and I'm afraid that it might hurt you more. But of course, the content becomes larger, so that I don't have a good perception on how students like that. So think about it and give me feedback. I'm not saying I'll listen to you, but but I'll surely want to hear. If you all convince me that no, this is not a good idea, it will hurt your points, then I will agree to that.
I think we can choose certain part like a contour or some kind of those things.
Yeah, how about
We
that?
can choose that
Yeah.
certain part, not like everything.
That's also reasonable.
I
Yeah,
think
good
that
point.
is
But
also-
think about it. Don't tell it now. Give it some thought and come back to me on that. Okay. Yeah. Yes.
Oh, so does that imply that the second midterm will be like the first? It will be just in class. You think?
Yes, it will be in class. What are the other options?
I think last when we were in classical, you had the bring to class problems,
Yes.
and then there was a 1 or 2 in class.
Yes.
So it'd be more. Would it be more like 5 or 6?
It will be 5 questions with 1 take home. 1 take home because I was forced to, like they forced me to make it 1 take home. I don't have a choice, I suppose. So 1 take home, or it may not be take home, it might be bring from home. It will be worked at home. I don't know how it's going to go. Like it's a little far. But so 4 questions remain. And what we are doing is differential equation at this point. Most of the problems are longer in general, and shorter questions you may not be prepared. I will have to make it trickier, or I'm afraid it might get trickier if I make short questions. If that makes sense. Yeah. But I can make short questions. It's my fear that it might hurt you. That's all. So give it a thought and get back to me. Okay. That's all. Anything else you want to point out?
It's okay. I think I'll back on 26.
Oh, yeah, you are also traveling, correct?
Yeah,
Yes.
that's
yes.
why if you cover from beginning, I mean it cover, that's.
Convince Pooja, we will make it the other way. She had moved the
No,
time. And now we can officially move it for you.
But I will back in 26, that's why, okay, I cannot say anything for that because I have few days. But if
But-
everyone agreed to move, then I'm okay with that, I didn't
Don't
have,
tell me, it's
So you
everyone.
want to move it forward?
like a 5th or 6th last time to the.
just don't include me in the anymore. Just get like to write the official email and all what you told me to do.
Right, exactly.
I mean, I wouldn't oppose, I'm fine either way.
Okay.
October 31st is also Halloween too.
Yeah.
I was gonna, if we had the exam on Halloween, I might come in costume. But that's the only thing I get to lose, it's fine either way.
So Ian invites everyone to his Halloween party and then we can have the examples.
Yeah, if you want to invite everyone, then that's okay.
Yeah. You guys like IPA, it's a beer.
I think Munster is okay for me.
So is it served free for everyone or they get? it?
Oh, if I have. Let's see, I think we get paid on the 31st, I think, right?
Okay,
So yeah, maybe.
you guys are rich.
Trying to pay.
Okay. Okay, so it stays open,
Mhm.
but don't, today is what? Today is, let's say 17. By Monday, this should be clear, right? Then we don't.
Tuesday
change.
I'm moving, that's why.
Yeah, but on Monday's class, whatever I write is the, after that, we don't move the date.
Okay.
Okay.
after the
And that
class
also
we
means
decide.
that I don't know how they will get involved in this decision.
I have their, we're in a group chat, so
Okay.
we can ask them,
So,
I should have asked. them.
yeah,
Yeah.
don't do it now. Like,
Oh, okay.
you guys are very instantaneous because of the modern generation. I think Jackson meets with me and I tell him to do something, he's doing right away. That time I say, go home and think and do it. No, it just starts doing it. So it's too fast for my generation. Okay, so we want to do Green's function. What is it about? So let's go back and consider a simple system, and this is going to be harmonic oscillator. So the topic is Green's function. Green is a name of a person. And I'm pretty sure you have heard of Green's function. How do you, what is Green's function if I ask you? What is Green's function?
It's kind of like it's a function that you would multiply, or I may not multiply, but you do on another function to represent kind of another.
I see what you're saying, yeah. Something more concrete? You know?
In Laplacian.
Yeah, good. But Laplacian, you said only Laplacian word. You have encountered it in electromagnetism, I suppose, or electrostatics probably. So in electrostatics, what is the primary goal? Usually?
Solve the problem.
Solve the Laplacian and give me the charge distribution. And I'll give you the electric field. So Laplacian gives you the electric field, correct? Or Maxwell's equation gives you the electric field. Notice again, give the charge density. Maxwell's equations gives you the electric field, correct? What's the simplest charge density you can think of? Point charge, right?
Yeah.
The solution for the electric field due to a point charge is the Green's function. You usually say the potential. The electric potential due to a point charge is the Green's function. Point charge, delta function, right, is the Green's function. If you want the general solution, you add up a lot of point charges, you get the general solution. Okay, so that's the idea. That if you can solve an equation for one delta function, you add up a lot of delta functions, you get any function. That's a very simple idea. We want to use that in the case of a harmonic oscillator, and later we will do this for electrostatics also. And I do harmonic oscillator because it's one dimensional, everything is simple. And we will later do this in 2 dimensions and spherical geometry and so on. That's how you generalize this. So again, this is only an example. So let's consider a spring connected to a mass. So let's say this is frictionless. So what are the forces acting on it? So let's say this is x equal to 0. So this is x, and there is a mass m, there is a spring constant k, and the force will be in this direction, right? If you stretch it to the right, the force would be to the left, and you would say Newton's law tells us that mass times acceleration, everything is happening in one direction. So I don't have to worry about the vector nature. I'll just say plus or minus will be accounted for. That's your right side. So it is mass times acceleration is equal to minus kx. That's your equation of motion for this system. I want to force this, or before that, maybe introduce some friction, which depends on the velocity. You can also have friction on this. So this is a velocity dependent force. You can say it is friction, but some velocity dependent force. And let's also say that you're actually moving it also. So you're forcing this oscillator. So that's f of t. Clear? So there is a spring with a spring constant. That is a natural frequency, and you are also oscillating it, or you're doing something. That is some function that is provided to you. That's called forcing. You're forced harmonics. And there is a natural frequency associated with this. This we will call it is k over m. So if there was no forcing, then it would nicely oscillate with this natural frequency. So that will be equal to plus f of t. That's a general system we can consider, but I won't have the friction, but I will have the f of t. So let's make it simple. So d square x over dt square is equal to minus k over m times x minus d over m times v plus f of t over m. So move things to the left. K over m is omega squared. So this I will call it omega squared. This, let's say, is gamma. And I'm going to remove the friction in our discussion today. So, but we have our equation as e squared dt squared plus omega squared, and let me write this. So the velocity dependence, first let me get the velocity dependence. So this is gamma d by dt plus omega squared times all acting on x as a function of time. And let's call this a of t, or a. And let me have this as minus a. Okay, so put the minus sign on the left. And this is a of t. In this way, you notice that this is this a of t is what makes it an inhomogeneous differential equation. If this was 0, if you don't force it, that's a homogeneous differential equation. So let's set gamma equal to 0 for now. So if we will not have this term. Right away from the beginning, I'm not going to have this. There might be homework problems where I will ask you to do this, but for now, I'm not planning to keep this. Let's have a homogeneous equation, differential equation. In this situation is minus plus omega squared x naught of t. So when I set a equal to 0, I will call the solution x 0 t, and that's equal to 0. And inhomogeneous this is okay, right? This is differential equation, that's the short form for that will be equal to minus and I'm not really giving you what a of t is. Whatever we are going to do, it's going to be very general. It will give me the solution for any a of t. So that will be the power of Green's function method. Again, the key would be if you know how to solve this equation, we will find out a way to find the solution to an inhomogeneous differential equation. Usually these are easier to solve. Homogeneous differential equation, they're easy, easier to solve, and then, but just using those, we will extend our methods to solve for an inhomogeneous differential equation. That's the basic idea. Let's go back and solve this very quickly. So, what's the solution to this equation? X0. That should be a familiar equation, harmonic oscillator. What are the solutions? Sines and cosine. And you will always learn many simple ways of solving standard differential equations. But if you can even guess a solution, that's good enough. Differential equations, there is no very concrete ways of this is the way and always give you an equation. There is no such way. If you know a function which satisfies this, that's a solution. That is all you need. So if you can guess it, that's great. So let's guess it in that way of saying it. So it is x naught of t. Sine and cosines are good enough. So let's say sine and cosines, right? So let's have it alpha naught sine omega t plus eta naught cosine omega t. Always, a differential equation is not completely specified unless you provide some initial conditions. Two conditions has to be provided. So here there's a second order differential equation, so two conditions. And this is a time, so it is not very useful if I have to tell you some information about the future. So it's good to tell the information right at t equal to 0 itself. If it's a position dependent equation, then you call it boundary conditions. Then you can really go on the both sides of a x line. In time, it is better to talk in terms of initial conditions. So let's say x of 0 is equal to, let's say, I have used a of t here, a, b, c, d, a, b, q maybe. And velocity at time t equal to 0 is equal to 0. I will change this a little bit when I'm actually introducing a forced oscillator, because it is simpler to just have 0. But if I have 0 in this case, nothing happens, right? It is a too trivial solution. So let's have it as q. So you put in those conditions. First of all, calculate the velocity also, x dot of t. That's equal to omega alpha naught cosine omega t minus omega eta naught cosine omega t. If x naught is equal to q, this implies that that t equal to 0, that's q.
Should
And
that be
t,
that sine omega t? The last line.
yes, of course, thank you very much. Good catch. Thank you. Well, and if I put t equal to 0, this is anyway 0, so this is equal to beta naught. And this implies that at t equal to 0, that's velocity, that's equal to 0, and that's alpha naught is equal to 0. So immediately you learn that x naught of t is equal to alpha naught is not there, so this is q sine omega t. That's a very simple way of solving a differential equation. Now the goal is that if you know how to solve this, can I solve this equation? And in this case, I would say, so here the condition was x of 0 was q. This is plus, right? Plus x dot of 0 is equal to 0. So these are boundary conditions. So this is not a plus with 0. This is a e. And here the conditions I want to put is x of 0 is equal to 0 and x dot of 0 is equal to 0. That's okay, because that is a forcing there. It can start from rest and it is perfectly fine. Okay, so that's our goal. And instead of solving this equation, one thing I can immediately point out, there will be some, this is just a nomenclature. If you want, let us say that, or let us find out if this is a unique solution or not for x of t. So let's say that you found a solution. Let's say let x1t be a solution for xt. That means I solve this equation exactly like I solved here, I guessed on it, and I'm able to find x1 t and or let's also say x1t and x2t be solutions to that. So that means there are two solutions. And then you say, is that possible that you can have two solutions? Usually differential equations have unique solutions. So how does x2 and x1 change? So write that down. So this is just giving you an idea of how inhomogeneous differential equations work. So saying this is also true. Like let's say that there are two such solutions. If that is the case, I can subtract them. Like let's play a trick that I subtract them, then I will have x1t minus x2t will be equal to 0, which is a homogeneous differential equation. Right, so this will satisfy x naught t. So the key would be that when I'm looking for solutions for x of t, I will always be off by a homogeneous part. Which is clear here. If I were to substitute x, whatever answer I get, if I put an x naught, if I add x0, that will give me a 0, so it doesn't change the differential equation. So whatever is the solution, so solution to x of t is always off up to x naught t. But that's not really good, because the whole idea of differential equation is prediction. If you're going to be not unique, then what's the point? Right? It's like saying you want to send a spacecraft to Mars and you don't know where it is going to land, there is no point in sending it. You want to be precise that the whole prediction has to be precise. So it doesn't mean that this doesn't mean that it is not going to be precise. It's just that these initial conditions will fix it. If you specify the initial condition, it is off by x dot t, whatever that is, that will get precise the moment you put in the boundary. So, however, initial conditions will quantify it or will make it or will take away the arbitrariness. It may not be very obvious how these things work at this point. That is my whole idea of doing this example. Look for how this changes, like how the initial conditions will come in and how the arbitrariness goes away. So the idea is that whatever solution you get, it's never unique. Like if I give this as an exam problem to you, all 5 of you can get 5 different solutions unless I provide a initial condition. The moment you put the initial condition, you will all make it correct. It is there in this also, if you notice, there is sine and cosine here, right? You can write it in exponentials, then it will look different. Like you can write 1 exponential, 1 sine. All of you can do various combinations, and that's perfectly fine as far as there are 2 independent solutions. But the moment you put in the initial conditions, all of you will get the same answer. Right? So that's very similar to that, maybe not completely precise what I'm saying, but it's in that spirit. So let's see how we are proposing to solve this. So let's instead of solving this equation, we solve another differential equation. That's what is called the Green's function. So Green's function for this differential equation is going to be, say, you keep the left hand side the same because we know how to solve for that. But instead, you don't solve for x. Instead, we define what is called a Green's function. A Green's function depends on 2 parameters, not on 1. So we are interested in solving for x. But Green's function depends on 2 parameters, t over t prime. But the advantage in a Green's function is that left hand side is more complicated. But the right hand side, instead of it being an arbitrary function, you make it a delta function. So that's saying that is only at one time it contributes. And it's a very special time, it's t prime. So it is like saying that you have this oscillator, you're actually forcing it, but instead of forcing it, you're only giving it 1 pulse. You're giving it at 1 instant, you're just pushing it. That's it, you're disturbing it at 1 time. And it's a delta function in the sense that only at t equal to t prime. It is precise that your touch is happening only at 1 instant. Is that clear? That's how you want to interpret it in time. If it was position and if you're doing electrostatics, this is a point charge. Right? And you remove the q also from there, and then that's what q will be the weight of the delta function. That is how you want to interpret. So that's how you want to solve it. But then delta function is not really a nice function, right? So it is 0 everywhere, and then it goes to infinity at one point. Very hard to deal with, but that is precisely the point. So how do we solve this differential equation? So this differential equation is nothing but, this is a way of saying that e squared dt squared plus omega squared times, let's say, g of t comma t prime is equal to 0 for, let's call this g left, for t less than t prime. So I have, this is my time. There is a special point t prime, which is a variable actually, but there exists a point t prime at which I am disturbing the system. For any time before t prime, the delta function is 0, right? That's your 0. So on this side, this is your old differential equation, I know how to solve that. On the right side, also I know how to solve it, so I'll repeat this. It's just repeating whatever I'm writing, but just for clarity, I'm going to write that, so this is right, so this is left. That's your right. That's my T comma T prime, that's also 0. This is when T prime is less than T. I know how to solve these equations. It's only at one point I don't know how to solve it. But that is okay. What I'm going to do is I will solve for these two. They will have two different conditions. Now there are two independent solutions, two different regions. So your alpha naught and beta naught will be different. But then I want to patch it at T equal to T prime. I want conditions that will patch them. Is that clear? So you have a solution on the left, you have a solution on the right, and you want some conditions that will patch them right at T equal to T prime. That will be our whole strategy in this whole game, right? So yeah, that's what it is. And let's say G of T comma GL, right? T prime is equal to, let me not call alpha naught beta naught, so let's say A cosine omega T or sine, right? So I said sine, so alpha. Yeah, no, alpha itself, so alpha L sine omega T plus beta L cosine omega T. This is the solution on the left side. On the right side, we have alpha, I need a new alpha right, yeah, alpha R. Notice these coefficients are not the same, they are independent solutions, so they are different. T prime is equal to T. We will solve for this, and now there are 4 constants, right? You have only 2 initial conditions. And already I have told you that there is going to be an arbitrariness in X naught also. So there are a total of 6 arbitrary constants at this point, right? 1, 2, 3, 4, and there are 2 coming from there. So it seems to be too much. So let's see how we proceed. So first I need some conditions at this point T prime. They will be called continuity conditions. So the patching is going to be done using continuity conditions. Now the important point is that continuity conditions are not provided by me. I cannot do that because every differential equation will have its own ways of working on it. So this equation has to provide me with the continuity condition. So I should be able to derive the continuity condition. Continuity conditions are not given to you, unlike initial conditions. That's a system providing the conditions, but these are the Green's function is I created this, right? It is not a system deciding this. So continuity conditions has to come from the differential equation. So what we do is we integrate this equation. So the first condition we will do is just integrate that equation with respect to, let's say, T. So this is the first condition. I'll write it. So this is dt, and I have to integrate in some region, but let me tell you which region I integrate. That's G of T comma T prime is equal to T. When will this contribute and when will this not contribute? If this integration limits are outside this T prime, it will not contribute. So let me pick my region of integration to be a very small region around T prime, where delta is a positive number tending to 0. So I do this integral from T running from T prime minus delta to t prime plus delta. Is that clear? Do the same thing here, t prime minus delta to t prime plus delta. Any questions? How? What is this integral equal to? That integral right side equal to? How do you do any delta function integral?
I'd love to go from 0.
Yeah, so you imagine there is a function here which is 1. Wherever t appears in that, or t prime appears in that, or t here, right? We are t appears, you have to replace it with t prime. But this is 1. So it is 1. So this is equal to 1. This is equal to 1 on the right side. On the left side, this is a total derivative, so it only gets contributions from the boundary. So this is equal to minus d by dt. One integral, one derivative remains. One of the derivative cancels with the integration, but then the limits has to contribute. This is t comma t prime, and this gets contributions from t equal to t prime plus delta and t equal to t prime minus delta. That's how you do the first integral. A total derivative gets contribution only at the boundary. The second term is nothing but minus omega square t prime plus delta dt of g itself. This whole thing is equal to 1. Is that clear what I did there? The first term is a total derivative. So after I pull out the derivative cancelling the integral, there is only first derivative remaining. It gets contribution from the two limits. Second term is an integral which is running only in the small region on this Green's function itself. And the third is 1. Clear? Right. This has to be a condition that has to be satisfied. If there is a differential equation, if I manipulate that, I should get conditions on that solution. Now, what can you say about the Green's function itself? Notice there is a function. This is a constant. Right? The second derivative of the function is giving me a delta function. Right? So what can you think of the function? What might the function look like at t equal to t prime? How do you get delta functions? Who's a function whose derivative is a delta function? What might it be? Other against it grades. Is it what? Is it grades? No. You're saying think of a let me draw this. I think I can erase this part, I guess. This. So if I have a, let's just have a x of t, and this is not x, let's say y of t, y of t and t. And if you have a function like this, what is y dot of t? It is a constant, right? Now, delta function looks like 0 everywhere, and then it goes to infinity, and then 0 everywhere, right? What should the function be here whose derivative is this? What should the function be? It should be 0 everywhere. Which function what is a function whose derivative is 0? Constant, correct? So it should be a constant. Right? It could be a constant here like this, like constant. On the right side also it is a constant, but it can be a different constant. Correct? So this could be a constant here like this. And it makes sense because this is discontinuity, but this is, if you were to make this continuous a little bit, you keep increasing, its slope increases to infinity. So that discontinuity is giving you this delta function. It cannot be at the bottom because then it would be a negative delta function. Right? So apparently some function like this can give you, let's do this better. So let's the exact function that does this is a step function. T minus t prime is equal to 1 or t greater than t prime, 0 or t less than t prime. Right? Okay. And this looks like this is 0 and 1. Right? So this is 0, this is 1, and there is at exactly 0, we don't define it at all. We don't know what that is. We are not defining the function at exact that point. So that there are some sensitive issues associated with that. One has to be careful, but we will not go there too much. But you should invoke or at least you should try to analyze those things. The derivative of this, we can do this using the idea of contour integrals also. You can verify this in different ways, but this will be delta function. That will be a feature that we will use. But we are not really needing this feature in here. Notice what we are saying is that the second derivative of a function plus the function is a delta function. What would happen if this actually went to infinity there? So let us think of a delta. Yeah. If there was a delta function on the left side, the derivative of a delta function is a different function. This is more, in very loose language, it is more infinite. It's a different kind of infinity than the delta function. This will be having an oscillation inside the delta function itself. It will go to infinity and then come to minus infinity. And then, so if you want, like delta functions very simplistically are thought of like this. A derivative of a delta function will be like this. You can think of taking the derivative of this, right? It goes to 0 here, like derivative comes to 0, that's just 0, and then again oscillates to come back. So you can imagine it like that, but the main idea is that derivative of a delta function is a different, if you want to call it a different entity, different beast. So whatever language you want to use. So we want to be aware of that. This is not equal to delta function, even though they are defined at one point, they are not equal. So we want to use these properties to conclude. So use these features, use these ideas to conclude that the Green's function here, there are two pieces. So I need a 1, or here you can say there is a function plus the second derivative has to be a delta function. If the second derivative has to be a delta function, the first derivative is already must be having a discontinuity. If you go one step further, you can have linear functions that give you that condition. So our condition would be that G, so the first condition would be that G of t, as t prime, is continuous at t equal to t prime. Try to contradict that. If it was not continuous, that means it will have a discontinuity. The first derivative will have a delta function. Second derivative will have a higher delta function, right? But we have a delta function on the right side. So it cannot have a discontinuity. So that's one way of saying it. If it has a discontinuity, the second derivative of that function will not be delta function, will be a higher derivative of a delta function. So that's why this has to be continuous. And the second would be if it is a continuous function, what is the integral of that function around that? So what can you say about the integral? This is t prime, and let's say this is this. So notice I only said it is continuous, its derivative doesn't have to be continuous. In fact, it will not come out to be continuous. So I'm showing that corner there, it means its derivative is not continuous. What is its integral going from this point to this point? So this is t prime minus delta, t prime plus delta. The integral will be this area. What can you say about its area as delta tends to 0? What is that area equal to intuitively? As I squeeze this, that will be 0, it will be a line, it will become a line. Line has a 0 area, right? As far as that line doesn't go to infinity. And we are saying it doesn't go to infinity because it does. If it goes to infinity, then its second derivative will be another feature. So we are saying it is continuous there, so there is no infinity there. So when I squeeze this, that will be really equal to 0. All that argument to show that this is actually equal to 0. That is that integral. Right? So this integral is 0. So you have. So the first condition is this is equal to 0. So g of at t equal to t prime plus delta comma t prime minus, or this is equal to g of t prime minus delta at t prime, which is the same as saying g left evaluated at t prime is equal to g of r evaluated at t prime. At no, t plus delta is r, right? So is that clear? Right. This condition that it is continuous means that the left and r we said there are two solutions. They should match, right? They should the value of the function that you solve for on the left hand side, the value of the function that you solve for the right hand side should match. Its value should exactly match on the boundary or at the boundary t equal to t prime, and its integral has to be equal to 0. This is dt g of t prime of t going from t prime minus delta plus delta is equal to 0. So those are the conditions. The second continuity condition comes from here. If this is equal to 0, then you have the derivative of the Green's function on the left hand side, t minus t prime evaluated at t equal to t prime minus the derivative of r minus L, right? I'm not making the same mistake. It's the right minus left, right? T prime plus delta. So this is r and this is left. Has to be equal to -1. The -1, I took this minus sign on the right side. Okay. So two conditions. What we are saying is, again, if I were to summarize what we did or the strategy, I introduced a new function, new Green's function. I said it will have two solutions, even though there is a delta function. One is on the left, one side of the delta function, one is on the right side. Two solutions, left and right. They have to satisfy this condition that their value should be the same at the boundary and their derivative should be discontinuous. The derivative should satisfy this. And the discontinuity is not any arbitrary discontinuity. it is a -1. Right, that value has to be exactly -1. If these two conditions are satisfied, that will allow us to solve for this alpha and beta L, at least two of them. There are two conditions here. And then there are two initial conditions, so 4 of them, but there are 6 unknowns. So we seem to be off still 2, but we will see that 2 of them combine. Okay, so clear how we are proceeding? Okay, so let's try to solve them now. So now that we have these conditions, we just have to put this in here. So I have to say right minus left is equal to 0. So right minus left at t equal to t prime. So I say alpha r. I'm substituting t prime, so that's sine omega t prime plus beta r cosine. That's fine. Right. And subtract the left. Is equal to 0, right? Instead of saying this is equal, I said this minus this is equal to 0. Do the derivative. So I'm going to do two things at the same time. I'll take the derivative and set the value to t prime. Okay. So the derivative of this is cosine omega t. So this is omega alpha r times cosine omega t prime. Second one is minus omega beta r sine omega t prime. Correct? And then subtract out the left piece. So this is omega alpha L cosine omega t prime minus omega beta L sine omega t prime, and the whole thing has to be equal to -1. That's my two conditions. Agreed? I can rearrange them. Is this part visible to you all?
Yeah.
Right.
Yeah.
Okay. So I'll collect the sine and cosines together. Alpha r minus alpha L times sine omega t prime plus beta r minus beta L times cosine omega t prime is equal to 0. And on the left, on the second equation, I'll first of all divide by omega all through so that it goes on the right hand side. And then I'm left out with alpha r minus alpha L times cosine omega t prime. And the next one is minus, right? So there's a minus and a minus. So this can be written as beta r minus beta L sine omega. That's equal to minus 1 over omega. Clear? These are two equations in two unknowns, where the unknowns have this construction that it's alpha r minus alpha. Like the combination can be solved for. Right, so let's solve that.
Second one, beta r minus beta L or beta L minus.
Yes, beta r minus. Thank you. Thank you. The thing. Right. Okay, so alpha r minus alpha L would be equal to solve this. Like this is a linear differential equation. What I do is first of all, how do you guys solve it? Solve the equation? Like you can take the determinant of the coefficients, right? So how I'm going to do this is the denominator will be sine omega t, the coefficients, cosine omega t prime and cosine omega t prime, and this is minus sine omega t prime. Take the determinant here, and the numerator would be replace this first column with 0 and minus omega. So 0 minus 1 over omega cosine omega t prime sine. Okay. The denominator is equal to minus 1, I guess, right? So the denominator is the determinant of sine square is minus sine square minus cosine square, that's minus 1. And the numerator is plus 1 over omega. So if this is overall equal to minus 1 over omega times cosine omega t prime. Think so.
You can just add this to and you.
Oh, if I added it, you get it?
Yeah.
But this is sine and cosine.
Oh,
Yeah, that's what I have to.
So you have to multiply, yeah, and many ways of doing it, honestly, yeah. So actually, you're right, so if I multiply. So this is, yeah, multiply this by cosine, this by sine, that's exactly what I got, cosine. And when it is sine, sine square plus cosine square is equal to 1, yes, same thing, exactly, yeah, however you do it, yeah. Right. And the same thing, you do this for beta r minus beta L is equal to beta R minus beta L is now, oh, I have to do the same thing. I have to put this, the new denominator is 1. So I have to do, what was it, sine omega t cosine omega t prime, and it is 0 minus 1 over omega. And this is, oh, and there is a minus sign. So it is 1 over omega times sine omega. This time positive. Okay, with me?
So how are you getting these determinants?
Oh, okay, so this is a way of solving linear equations. Let us say you're solving for ax plus by is equal to alpha and cx plus by is equal to beta, right? Suppose you have two differential equations and then x would be equal to, look for the coefficients in front. So that is a, c, b, d, right? Is that clear what I did? I looked for the coefficients and wrote that as a determinant. And now what, and that appears in both a, b, c, d. That appears in both x and y. But when it comes to x, what is the determinant you write on the top? The same one, but the one column that you're solving for is x. Replace that with alpha and beta. Is that clear what I did? And here I replace the opposite. A, C. Okay. That's a universal way of doing it. It's easier to remember, but you can always add, multiply. That is much more intuitive in sense. Yeah. Okay, so that's your solution. So once you have that, you pretty much have your solution, correct? So let's have GL and GR. So now we have alpha R and beta R. There is only one of them we can solve, right? So I'll solve for R, right? The right will be solved in terms of left. So GL remains the same. Alpha L sine omega t prime plus beta L cosine omega t prime. And the R, I'm going to write it in terms of L. Since there is an L which is exactly the same, so it is alpha L sine omega t plus beta L cosine omega t prime plus now I have to put in the actual values. Alpha R is minus 1 over omega cosine omega t prime omega t prime times cosine omega t. Or did I draw like this wrong? This is wrong. Sine. Sine omega t. Theta r is cosine. Is that clear what I did? I'm basically substituting for alpha r is equal to alpha L plus this inside here. Right. So alpha L gives you the same, and so GR actually is equal to GL, and this combines, right? So this is equal to minus 1 over omega sine of omega t minus t prime. Right. But in the beginning I told that the solution for your differential equation will be off by a homogeneous solution. This is a homogeneous solution. So who cares? There's already an x naught, I can combine it with x naught. Right? So this is an arbitrariness which will be fixed by your initial conditions if you want, which we will accommodate in x in principle. Right? So I can always subtract or remove. So this is homogeneous. So g of, let me write that again. So first of all, g of x, now I'm writing it everywhere. G of t comma t prime is alpha L sine omega t prime plus beta L cosine omega t prime and minus 1 over omega sine of omega t minus t prime. Correct? That's my, oh, that is a mistake, right? This is only for R. Sorry, I think I went. So this is for t greater than t prime. And for t less than t prime, it is equal to alpha L sine omega t prime plus beta L cosine of omega t prime. Agree? So it seems like there is a piece that is 0 on the left, exists on the right side. I can use the step function to capture that. I'll say that this is alpha L sine omega t prime plus beta L cosine omega t prime and minus 1 over omega step function, which has to contribute only for t greater than t prime. So this is t minus t prime times sine omega t minus t prime. Did I write that correct? Yes. So it is t greater than t prime. Remember, this is 0 when it is less. So this way of writing that there is something on the left, something on the right, I have captured it by writing it in terms of a step function. Okay. This is homogeneous. So this satisfies homogeneous differential equation. And we already said that any inhomogeneous differential equation is always off by a homogeneous part. So I can as well drop that. Or I can keep it and it will later get absorbed into the x naught solution, because there is an arbitrariness anywhere and anyhow in that. What, for simplicity, what I will do is that I'll drop that because you only need a particular solution. If you don't feel comfortable about that, you can keep it here and later it will get absorbed into the x naught. So notice there were 6 arbitrariness. 2 of them went away just because it is a homogeneous part of the differential equation. which we will account for later when we are talking about x naught. The initial condition will bring it back if you want. So that's your Green's function, but that's not our goal, right? Our goal is to solve for x of t. Right? We have only solved for a delta function, and that is got by, if you have one point charge, the solution for a point charge, electric potential due to a point charge. If you have 5 charges, how do you do it?
Just adding the.
Adding them up, right? So adding with the appropriate charge in front, right? Same thing, you have now 1 point time solution, you add them up, which is basically integral. Right, so x of t would be, we won't do it now, x of t would be equal to just integrate minus infinity to plus infinity dt prime. This is t prime getting integrated with g of t comma t prime, and you weight it with a of t prime. This is like multiplying the charge. This is your electric potential, this is your charge, and you sum it up. Right? That's your Green's function ID. But remember, always this differential equation is off by the homogeneous part. So I have to provide that it is some x naught in front, which has the initial conditions to fix that. And if I had kept this, if you were not satisfied with dropping this completely, then this would get into this. So there will be 2 x naughts coming in. So either you can say you are dropping it here, or keep it and it will collect in here. It will just be a constant that changes. So I have 2 constants here. I have to fix that using my initial conditions, and we have to process this also. Let's come back on Monday and do that instead of me hurrying at this. Okay, I'll stop here. Thanks.
And that method is known as Fermat's rule. It's using matrix to solve the equation.
Oh, what is it called? Kramer's.
Yeah.
Kramer's rule, yeah. Kramer's rule.
Oh,
Okay, good, thank you. How do you close?
oh, you did both?
So Rocky, which university are you from?
At University of Dhaka.
You're also?
Yeah, she was my classmate. Yeah.
Oh, yeah, I think.
Oh, should I in?
Huh?
Should I in the stuff of the meeting?
Just end it. Is that what you asked?
Yeah.